I welcome you in this fourth lecture on Laplace transforms. Today we'll recapitulate the Laplace transform, and I believe that you have already done a course on Laplace transform from the Department of Mathematics. So Laplace transform, so far as concerned, is very much useful for the analysis and design of linear time invariant systems. Linear time invariant systems. So for linear time invariant systems, we use Laplace transform for analysis and design. Basically, Laplace transform converts a time domain signal. It converts a time domain signal into frequency domain. We'll see how. Say, for example, all it means is that if we have a signal as a function of time, which is in time domain, will be corresponding to it when we apply Laplace transform on this function, we will get another function, f of s. So from time domain, the variable here, the dependent variable, here is time, and the dependent variable here is s. S is frequency. S is basically sigma plus j omega. S is a complex number. Sigma is some constant, and omega is basically your frequency. So if we have a function f of t in time domain, and if we apply Laplace on it, we get another signal which is f of s, and it is a function of s. Earlier it was a function of t, now it's a function of s. So we are able to convert a time domain signal into frequency domain. There are various advantages of using such transformations. We'll see as we go down the line. Now, as I said, it is used for the analysis and design of linear time invariant LTI systems. We'll first try to understand what LTI systems are. Say, for example, we have a system and we apply an input x of t to it, and let us say yt is the output of this system. Now if the system is linear, what does linear mean? Then we'll come to time invariant. First thing is linear. So linear would mean, say for example, when I am applying xt, the response is yt. Corresponding to xt, our response is yt. Now say for example, I apply a signal which is a times xt to the same system. The response would be a times yt, where a is some constant. Further, say I have the system, and when I apply a signal to it, I get some output. Say for example, my input is x1t, and corresponding to x1t, our output is y1t. Now if I apply x2t, corresponding to x2t, the system gives us output as y2t. So for x1t, when I apply x1t, the response is y1t. When I apply x2t, the response is y2t. Now if I apply a signal which is a times x1t plus a1 times x1t plus a2 times x2t, the response of the system corresponding to this input signal, this is the input that we are applying to the system, corresponding to this, the response would be a1 y1t plus a2 y2t. So this would be our output. So this is what linearity means. So this basically obeys superposition principle. Now coming to the time invariant. What are time invariant systems? Time invariant systems. Say for example I have a system. I apply xt as an input signal to it and I get yt as an output. Now if I apply x t minus some delay t, I'll get y t minus t. So if corresponding to xt, my response is yt. Corresponding to xt minus t, the response of the system is yt minus t. So time invariance means whether we apply input to the system now or t seconds from now, that's after a delay, t seconds from now, the output would be identical. Except for a time delay. So let me try to make you understand it this way. Let us say, for example, we have a system. We have this as our system. We are trying to understand time invariance. And say, for example, to this system, our input to this system is this signal. And let us say that this system behaves like an amplifier, an invariant, time invariant amplifier. So the response would be something like, we'll be having the amplitude higher than the input. So this is our input, our output is this. Now to the same system, if I apply a delayed response, for example, if I apply to the same system, if I apply the same input, if it is xt, this is t, say for example a delay of t, so this input is x t minus t, capital T. So we are giving a delay of t seconds. So if we apply this to the same system, the output in this case would be an amplified but delayed version. So this is what the output would be. Output would be after some t seconds, after a delay of t seconds. So now you see, when we apply this as the input, xt as the input, we get this as the response. We are applying xt, we get yt. And when we apply xt minus, when we apply x t minus t, the response is y t minus t. So this is what time invariance means. So all in all, in this lecture or in this course, we'll discuss linear time invariant systems. We are discussing linear time invariant systems, LTI systems. The analysis of these systems is being done using Laplace transform. So now let us try to understand the final version of a linear time invariant system. Let us assume that it is a linear time invariant system. We are applying some input, we get some output. Now if the input we apply is a1 x1t plus a2 x2 t minus t, the response would be a1 y1t plus a2 y2 t minus t. So we are applying a delayed signal here. Corresponding to this delayed signal, we get a delayed response. We are applying a signal x1t, we are getting a response y1t. So this is what a linear time invariant system is all about. Now, any linear time invariant system can be characterized entirely by a single function called as system impulse response. System impulse response. So what does that mean? That means, say for example, I have a system. I apply an impulse. An impulse is designated by del of t. When I apply an impulse to the system, the response or the output that the system produces is called as impulse response. So this h of t is basically impulse response. Response to the impulse. When I am applying an impulse, here I am applying an impulse, and the output that I get is h of t, which is called as the impulse response. And if we know the impulse response of a system, we can characterize it entirely. Now, this is the system impulse response. Now, say for example, I have this system whose impulse response is h of t. And to this system, I apply an input x of t. What is the output? As I said, the system can be completely characterized if we know the system impulse response. So the impulse response here is h of t. So what is the output yt? So yt in this case is simply the convolution of xt and ht. That is, yt is xt convolution we represent by this asterisk sign, convolution with ht. So if we know the system transfer function or the system impulse response, and we know the input, we can obtain the output by using this equation. Again, I'll say, so output is nothing but the convolution of the input signal and the system impulse response. So what is this convolution? This is basically an integral of the form xt tau h t minus tau d tau minus infinity to infinity. So this is our convolution integral. So this represents x is convolved with h. So as can be seen, it is difficult to evaluate this integral. So what we do is that we use frequency domain. So from time domain, we move to frequency domain. So these linear time invariant systems can be characterized in frequency domain by transfer functions. Or by transfer function, which is nothing but the Laplace transform of system impulse response. So what we do is that if h of t is the impulse response, we take its Laplace and we get something which is called a system transfer function. This h of s represents a system transfer function. So where h of t, as I said, is impulse response. So I repeat, impulse response is, what is your impulse response? You have a system, you apply an impulse, whatever is the output, whatever is the response is called as system impulse response. So this is in time domain. So in frequency domain, what we do is that we take Laplace of this system impulse response, and whatever we get is called as HS, system transfer function. This is system transfer function. So another thing that I need to tell you is that for continuous time signals, we use Laplace transform. Whereas for discrete time signals, we use Z transform. This is what will be taught to you in your digital signal processing subject. Probably in your 7th or 8th semester. So coming back to our topic, if I have a system with system impulse response as xt, and if xt is the input signal, in time domain the output is given by the convolution of xt and ht. This is the convolution symbol, as I said, convolution symbol, which I said is basically an integral minus infinity to infinity x tau h t minus tau dt d tau. And now if we go to frequency domain, instead of ht I'll be having h of s, because I take Laplace of h of t. As I said, Laplace of h of t is h of s. So instead of h of t I'll be having h of s. Instead of x of t I'll be having x of s. Instead of y of t I'll be having y of s. So xt, we apply Laplace and we get x of s. ht, we apply Laplace and we get h of s. Yt, we apply Laplace and we get y of s. Now, how I said xt and yt, they are related by this expression. Yt is xt convolution of ht. Now, how are these related? How is xs related to ys? Ys is simply xs into hs. So that's where the advantage lies. This is basically an advantage, that in time domain you have to solve a complex integral, but in frequency domain it is simply a multiplication of two quantities, xs, the input signal in frequency domain, and hs, the system transfer function. So simple multiplication of xs and hs gives us the output ys. So ys is nothing but xs into hs. That's what makes it easy for the computations and calculations. So another advantage of using Laplace, is that it changes or converts differential equations. It converts differential equations into simple algebraic equations. Say, for example, we have a differential equation d2y by dt square plus 5dy by dt plus 8yt is equal to, say, for example, 15 e to the power minus t. Now, in order to solve this differential equation, it is difficult to solve this differential equation. So what we do is that we use Laplace transform. So when we apply Laplace on it, when we apply Laplace, what happens is that this differential equation gets converted into an algebraic equation. For example, this differential equation will get converted into s square y of s. I assume there are no initial conditions or there are zero initial conditions. I neglect the initial conditions. I neglect initial conditions. So on applying Laplace, what we'll get is s square 5 times sys plus 8 times y of t, Laplace would be y of s, and 15 Laplace of e to the power minus t would be s plus 1, 1 over s plus 1. So it becomes basically an algebraic equation, and solving it would be much more easier. For example, we can write it as s square plus 5s plus 8 if ys is taken out, 15s plus 1. And now I can write ys is 15 s plus 1 s square plus 5 times s plus 8. So this is our y of s. The Laplace of y of s is basically Laplace of y of t. This is y of s. So we are able to find the output, basically the Laplace of the output. So in order to find yt in time domain, we need to take inverse Laplace of ys. So that's how it makes things simple. Now let us again discuss Laplace of some basic functions. Laplace transform of some functions. We know by definition Laplace of any function f of t is 0 to infinity e to the power minus st f of t dt. And on solving this integral, we'll get a function which is simply a function of s. So this is how we represent it. Now let's take a few examples. Let us try to find the Laplace of unit step function. The first example is unit step function. As we know, a unit step function can be written as u of t is 1 for t greater or equal to 0, and u of t is 0 for t less than 0. So mathematically this function looks like, if this is the time axis, for t less than 0 it is 0, and for t greater or equal to 0 it is, say for example here it is 1, then it is 1. So this is a line basically parallel to the time axis. So this is our unit step function. Now let us try to apply Laplace on it. So Laplace of, as I said, Laplace of f of t is 0 to infinity e to the power minus st f of t dt. So Laplace of our function which is unit step u of t. Unit step function is being represented by u of t. So Laplace of u of t is 0 to infinity e to the power minus st. And what is ft? Our ft is nothing but ut. Now as we know, this ut is basically equal to 1 for t greater than 0. For t greater than 0, for 0 to infinity, for these values 0 to infinity, our u of t is 1. So I can write it as 0 to infinity e to the power minus st 1 dt. So it is integration of e raised power minus st would be e raised power minus st upon minus s, limit is 0 to infinity. So I can write it as minus 1 over s e to the power minus st 0 to infinity. So I can write it as minus 1 over s. If I substitute upper limit, it will be e to the power minus infinity, and if I substitute lower limit, it would be e to the power 0. So it becomes minus 1 over s 0 minus anything raised power 0 is 1. So this is 1 by s. So all in all, we have seen that Laplace of u of t, which is a time domain signal, is nothing but 1 of s, which is in frequency domain. Now let's again take another example. Example number 2 of unit impulse function. Unit impulse function. So an impulse function mathematically can be shown as, if we plot time versus magnitude, this is value 1. So this function is 0 everywhere. This is 0 everywhere except at t equal to 0. It has a value. So this function can be written as del of t is equal to 0, t not equal to 0. It is 0 everywhere except at t equal to 0. So now let's try to find its Laplace. Laplace of del of t is 0 to infinity e to the power minus st f of t dt, and our f of t this time is del t, Dirac delta. And so far as this integral is concerned, this integral basically represents area under the pulse, or area under the pulse, which is nothing but 1. So Laplace of del of t is 1. Now let us take another example. Laplace of an exponential function. E to the power minus alpha t. Let's try to find its Laplace. So Laplace, so our f of t is basically e to the power minus s. Our f of t this time is an exponential function where alpha is some constant. So Laplace of this function would be 0 to infinity e to the power minus st f of t dt, which can be written as 0 to infinity e to the power minus times s and alpha then t dt. So we can write it as e to the power minus s plus alpha t minus s plus alpha, because integration of e to the power mx dx is nothing but e to the power mx by m. So that's what we are doing, plus some constant of integration. So it is e to the power minus s plus alpha, and the limiters here are 0 to infinity. So this can be written as minus 1 over s plus alpha, and then you have e to the power minus s plus alpha with upper limit as infinity and lower limit as 0. So this would be minus 1 over s plus alpha e to the power minus infinity e to the power minus 0. This is minus 1 over s plus alpha. E to the power minus infinity would be 0. E to the power 0 would be 1. So it is 1 over s plus alpha is the Laplace of e to the power minus alpha t. These are some of the very basic or simple examples. Now let me show you the Laplace of functions along with their values. Rather, let me use that Laplace table. I will import this table from the already saved document, which is a PDF document. Let me upload that PDF. Then it would be in WhatsApp documents, Laplace table, done. This is your, let me undo it. Let me again move back and let me attach it here. Attach PDF from WhatsApp documents Laplace table. Done. This is what it looks like. Let us try to understand it. Okay, let me erase the text. Let me delete it, cut. Let me cut this as well. Let's cut this as well. Cut it as well. So this is what it looks like. Laplace of 1, as can be seen, Laplace of 1 is 1 upon s. 1 is your unit step, basically u of t. Laplace of t to the power n is n factorial s divided by s to the power n plus 1. Laplace of sine at is a by s square plus a square. Laplace of cos at is s by s square plus a square. This is what you have done in your mathematics. For practice, you can again solve these functions. So that's all we have for the day. Good day.